This presentation does not attempt to show new discoveries or unexpected results and so on. In fact, it's very simple, and it tries to look from an uncommon perspective all problems in environment and ecosystems, hoping that this enables a more holistic view of similar things. Okay. First of all, let's have a look on some properties of water. Water has a molecule with a high energy of formation. It is very stable. Maximum density is at 4 degrees. It is relevant in some cases for vegetation in cold areas. Extremely high evaporation heat, and also fusion heat, and also specific heat. All these kind of issues related to heat transport are very relevant in water. The dielectric constant is rather high also, which shows that it's a good solvent. And well, thermic conductivity, surface tension are also rather high. And well, which are the more relevant functions to our purpose of water? We can distinguish at molecular scale. It's a quasi-universal solvent. It is very important to enhance chemical reactions. But it is not our job now. At the ecosystem scale, it works mainly as facilitator. Facilitator of what? Of transporting nutrients and chemicals, providing turgency, which is not a little thing, and mitigating solar energy dissipation power, which is very important. The three later are using this capacity of heat pump of water that can catch energy from one side and transport to another, changing temperature and so on. Well, let's keep some minutes in these issues of what we call here thermodynamics essentials, because there is a lot of confusion in most cases. Everybody knows what is energy, a bit of confusion in entropy, and almost nothing about exergy. Well, taking into account that ecosystems are open systems, This means that there is a flow of energy and information through them. And that they are what is called autogenerative. So with this energy they grow. And by growing they produce entropy. Let's try to explain this a little more. By the fact of being open, this means that in a stationary state, the energy flow is constant through the system. But the energy flow per se does not inform us about the energy which is work at one moment in concrete. And for this reason, the concept of exergy has been grown recently, or not so much recently, but well. This means the energy appointed to do a specific work. For example, in ecosystems, the energy responsible of photosynthetic issues is a very little part of the radiant energy. And this little part is what we call exergy, okay? Well, exergy, when it works, it expands because very concentrated energy is and very high grade energy is very concentrated. When it works, it expands and dissipates. This dissipation is entropy. Entropy is not a special thing, it is a state dissipated of the same exergy when it is working. I think it's a very simple way, perhaps not so much thermodynamically exact, but we can understand better by this way, I think. So the important thing is that in doing work, exergy diminishes and entropy increases by the fact that I said to now. Well, this has some consequences, and is that we call exergy entropy cycles. So this means that in order to work, the first thing is to provide the necessary exergy. And the second step is to consume this exergy doing work. The third part is generating entropy. And the fourth, which is the most important, is disposing the entropy. Because if entropy is not disposed away off the system will be clogged from entropy and nothing more could be done. So the only way to ensure that the system works is a system that takes the entropy off. Okay. Let's go to an ecosystem. Very simple. An ecosystem is the sun that provides exergy. This exergy produce or works in living gross primary productivity, and in doing that it produces entropy, and this entropy is heat, which is the way most dissipated of energy, heat and matter. This matter is oxidized carbon. Okay? The gross primary productivity is the energy sources for all the consumption processes, which are an incredible cycles, such these ones, microcycles that makes some kind of food webs and how to say encapsulated cycles in this system. And by this way, the dissipation of energy from GPP becomes dissipated very little by little and very efficiently. It produces heat and respiration, And all what is not respired and produced heat in this way is left to the soil, is the litter. The litter and the remains of animals and so on. The soil is the site where entropy is deposited, and is the way the system can go ahead. But that needs water. The work of the soil, and particularly soil organic matter, in recycling needs water, and the function is to give back nutrients and water to the vegetation. But the crucial role of the soil is seen here as the receptacle of entropy that can be reused and reused by very complicated food webs. Okay? Well, let's go now to a very simple, now the former are concepts. Now let's look at a very simple proposal from Budyko, which was I think was a Russian physicist, I think, and he tested a plot with two axes in upsides is the index of aridity, that is potential evaporation to rainfall. In ordinates is the ratio between evaporation and rainfall. Okay? Well, very simple. But the thing is that this plot has two lines, two boundaries that cannot be surpassed. One is what is called this one. This is the water limited boundary. What means that? It means that it's impossible to evaporate more water than rainfall. Okay? It's impossible to evaporate more water than rainfall in a site. And this boundary is when the evaporation versus rainfall is 1. And another limit is that evaporation has to be equal to potential evaporation in values less than 1, because because in the abscisse line we see that there is a point in which aridity index becomes 1. So from here to the right it increases, from here to the left decreases. This means that this point is very important because from this point to the left energy is limiting. Here water was limiting, but here is energy which is limiting. So if in this plot we put a lot of watersheds in the world that Budyko took, the plots follow this line. So it is not exactly this, but in this area the variability is very high. This has a lot of useful results that can be achieved about the behavior of runoff, because in these situations runoff is almost absent, and in this situation runoff is very high. There is even recently works that tends to tell that this behavior has also a thermodynamic explanation. But let's forget all this for the moment. What is important for us are the extremes. What happens in the extremes? So in the extremes there is a potential evaporation very high here and very little here. So let's see. There is a very known relation that is known as Bowen ratio, which is the ratio between sensible heat flux to latent heat flux. Sensible heat flux is the heat which is sent to the atmosphere from the soil, which is very heated. And latent heat flux is the energy used for evaporation, which is up to the atmosphere. So this means that if sensible heat flux is very high in relation to latent flux, means that the system is very inert. The role of water is very little, because there is very little water, and almost all energy transfers are made by the solar dissipation. If latent heat is very high, the organic and water control is very high. Okay? So we postulate that in this extreme, Bowen ratio is very high, and in this area, Bowen ratio is very little. In fact, normal values in deserts of Bowen ratio is 10, semi-arid is between 2 and 4, I think, and here is less than 1. So, let's see another results from another relevant paper concerning temperature. In this plot we see it It is one day in all Andalusia with thermical data from satellite. And we see that we call the wet edge here, which is the temperature lower, and the dry edge here. And this means that in this part of here the values are NDVI. So NDVI is in vegetation density. And in vegetation density areas, the span, the span is very high. This means that when the NDVI is low, there are sites which remain humid because there is water, and sites which is no water and is very hot, very high temperatures. But as soon along as NDVI increase, the span between temperatures decrease. So when there is a lot of vegetation, temperatures tend to converge in very low values. This is what means this graph, which is congruent with this idea that in the dry end of the Budyko curve predominate physical aspects in the forces. Well, let's see now what happens in a real vegetation near here, near from the excursion tomorrow. It is a mountainous area, which is the ridge, and all this is Stipa tenacissima, bush, graminean bush, and it is the sunny slope, and it is the north slope. Well, the first thing that we see is that the color of the soil is more dark than here. This means that it is a little bit more organic matter. And there is a structure very apparent. A structure not apparent in the ridge, but very apparent in the slopes. Let's see now a more approach about that. It is a little plot from that area. Here is the upslope is in this direction. The scale, you can see these 2 meters of the ton of plots. And you see how the tussocks are. They are green upslope, and they are gray downslope. This is very similar of what happens in many other areas in Tiger Bush and so on, and in micro Tiger Bush. This system is growing, it's auto-generating, getting water from the bare areas and growing in this direction and leaving behind all which is dead, and is entropy in this case. So this system it shows that at a very micro scale the growing can go ahead because entropy is leaving behind and is dispersed by sun and by wind. Estimated Bowen ratio here may be to 7 or so similar. let's go to the wet side, wet limb of the Budyko curve. Here is Tierra del Fuego, in an area called Ventura, which is a Bowen ratio of 0.25, and in which the energy to evaporate is very low. Well, what happens here? We see these forests are forests of Nothofagus. Nothofagus is similar to Fagus, but in subantarctic areas. Well, which is relevant is that you can perceive big marges, big areas of forest, which are with some kind of small wounds, some areas without forest, and below that there is big masses of mosses, of turf. So this situation suggests that this kind of work of woods are in a very fragile equilibrium with the turf, with the mosses, because, and this we have proof of that, if there is, for example, afforestation made by men in large areas, these areas become prey of mosses, and never trees can recolonize that, because it's an example of ecosystem which is clogged by entropy. Okay? Well, let's summarize now very short way. Concerning ecosystems, they are dissipative self-regenerating systems with, you can distinguish the following attributes. This kind of intricate networks of energy entropy cycles, which increase the efficiency, increase terribly the efficiency, and the energy dissipation is very little by little. And the ultimate waste disposal as is in the soil. And water is a key element for all that runs or not runs. This between Scylla, which is scarcity, to Charybdis, which is turf. Okay? And what happens with man and the agriculture? Some regularities appear. One, and most important, is decoupling the exergy from entropy disposal. Because the role of soil is eliminated in this system, in our agriculture, because all which is structure is eliminated. Plants are with less wood and more leaves and so on. So decoupling exergy from entropy is the first thing. The second thing is coarsening spatial structure. This kind of spatial structure, very, very detailed, we have seen, is very useful to be able to support and to react to the solar dissipation, which is the main problem there. And the third here is hindering ecosystem regulation capacity to external dissipation factors. So if we decouple the production from the entropy recycling, the capacity to resist difficulties such as solar dissipation or too much water are impossible. So these are some examples more, but finally, what we can expect from industrialization of agriculture, it's more expensive, more unstable, less safe for health, and shift all agriculture to nature gardens, as happens in Europe now. And this hides the problem in reality. Thanks very much.